prosthetic limbs. Matthew.
Thank you. Good morning. I'll be presenting a research study conducted by Chris Kelly and Maria Gershutz comparing skin temperature and moisture buildup between two prosthetic liners. Heat and perspiration are common problems associated with wearing and using a prosthesis. The socket and liner encapsulate the limb and act as a thermal insulator. Therefore, heat generated in the limb cannot escape into the environment, resulting in elevated skin temperatures. This could lead to discomfort, moist skin, which is softer and more susceptible to injury, and suspension problems because moisture can allow the limb to slide within the prosthesis. Some products exist to address these issues, for instance, wicking materials, which are designed to pull moisture away from the body. The downfall of these systems is that they are reactive, and the benefits are not provided until after sweating has begun. So our proposed solution was to develop a passive liner system with increased thermal conductivity and heat capacity. The system becomes proactive rather than reactive by delaying the onset of sweat. And this is achieved by incorporating phase change materials developed by Outlast. Outlast phase change materials are a wax-like substance that melts around normal skin temperatures. A phase change transition is a constant temperature process that absorbs or releases a significant amount of thermal energy. So products incorporating phase change material take advantage of this process by absorbing excess heat from the body and keeping the skin temperatures the same. So as depicted in the graphic here, as excess heat is generated, the phase change material melts and keeps the user in an ideal comfort zone. So our research study was initiated by claims of patients wearing a prototype PCM liner. They reported of a more comfortable temperature environment and also less moisture buildup inside the liner. So the purpose of our study was then twofold. First, we wanted to evaluate the effectiveness of the PCM liner to regulate temperature and control perspiration compared to a non-PCM liner. We hypothesized that the PCM liner would reduce temperature changes and perspiration. The second aim was to determine the best instruments and procedures to measure these outcomes in preparation for a larger study. To measure temperature, we use a K-type thermocouple. It has a conversion module and a multimeter. And we measure temperature at one location on the residual limb, the posterior calf, as shown in the figure here. And temperature measurements were taken throughout the different phases of the testing procedure, which I'll get into in a minute. To measure skin moisture, we used a dermal probe meter, and this measures surface electrical capacitance. This was performed at 5 sites in the residual limb: the posterior calf, the back of the knee, medial, lateral, as well as the distal end. And these measurements were taken before donning and immediately after doffing the prosthesis. 6 transtibial amputees participated in the randomized crossover study, comparing a PCM liner to a non-PCM liner. Each participant would complete the activity, which was walking on a treadmill at 2 self-selected paces. And temperature measurements were taken before, during, and after the activity, and skin moisture measurements were taken before and after the activity. So a little bit more detail on that. The testing was divided into 3 phases: pre-activity, activity, and post-activity. Pre-activity began with initial temperature and moisture measurements after the limb had been out of the socket and liner for 5 minutes. Additional temperature measurements were taken after donning the liner, after the temperature reached steady state with the liner on, and after the temperature reached steady state with the socket and liner on. Temperature measurements were taken every 30 seconds, and steady state was considered reached when 3 consecutive measurements were the same. The activity portion included several temperature measurements. These were recorded after the patient stood up, after they walked at a self-selected slow pace for 5 minutes, after walking at a self-selected fast pace for 5 and 10 minutes, and again after a cool-down period where they walked at a self-selected slow pace for 5 minutes. Post-activity measurements were taken sitting down immediately after the treadmill walk, and again 15 minutes later. After that, the prosthesis and liner were removed, and final skin moisture measurements were taken. Then there was a 30-minute rest period before beginning the next treatment. So, getting into some of the results now, starting with temperature. Here, the average temperature for each measurement point throughout the collection procedure is shown. And the data indicated the following trends. First, donning either liner initially reduced the temperature. Second, activity increased skin temperature. However, third, the PCM liner exhibited lower temperatures. Particularly of interest is this area between 10 and 15 minutes. This would have been the last 5 minutes the patient was walking at the self-selected fast pace. And here we see the largest deviation between the data. And also interesting is the PCM curve exhibited almost no change in temperature during this time. Also comparing the slopes of the two data sets, found a 33% reduction in slope associated with the PCM liner compared to the non-PCM liner. And at the end of the activity, there was a 1.78 degree difference between the two. This may be clinically significant. Peary deduced from the literature that a temperature increase of 1 or 2 degrees was responsible for the reports of thermal discomfort reported in the literature. And finally, post-activity measurements were relatively stable for the PCM liner. Comparing the two data sets, there was a ½ degree more temperature increase associated with the non-PCM liner compared to the PCM liner. Looking now at the skin moisture results, here we have the average percent change in surface electrical capacitance at each of the 5 sites tested. Higher SEC values indicate more moisture on the skin surface. And taking the average across all 5 sites, we found a 20% reduction in the skin moisture compared to the non-PCM liner. And in fact, 23 out of 30 comparisons favored the PCM liner or indicated no difference between the two. So from the results, it was shown that the PCM liner buffered temperature fluctuations. This was evident by the lower temperatures during the activity period, as well as the more stable temperatures post-activity. There was also less moisture buildup for the PCM liner compared to the non-PCM liner. And the lower skin temperatures associated with wearing the PCM liner could be an influencing factor on this outcome. And finally, the small sample size of this preliminary study limited any statistical analysis. So you may remember from an earlier slide that a second aim of this study was to determine the best instruments and procedures to measure these outcomes in preparation for a larger study. And so what we've learned from this is improvements to our collection instruments can improve the procedures. So starting with the thermocouple we used had a very stiff probe, the wire specifically. And so as you can see by the picture, we had to be careful to route that wire around the knee. If it got behind the knee during knee flexion, it would cause the probe to snap and we'd lose the temperature data. It was also, the thermocouple unit was also capable of discrete sampling, so a continuous temperature profile could not be obtained. But probably the most problematic is that it was sensitive to movement, which became disruptive during the activity portion. So as the person was walking on the treadmill, as it became time for a temperature measurement point, we had to have them step onto the sideboards of the treadmill and remain still while the temperature was recorded. So since this procedure, we've identified a new thermocouple probe with a more flexible wire, capable of continuous sampling, and is much less sensitive to movement. We also only measured temperature at one location on the residual limb, but a better understanding of heat transfer could be obtained by layering thermocouples. So we thought, putting one between the liner and socket, as well as on the outside of the socket, and in the ambient room temperature would be beneficial. Sometimes upwards of 60 seconds holding it on the patient's skin. And it was also very sensitive to contact. So if you were sitting there and you're 30 seconds into your measurement and slight movement occurred and you lost contact, you essentially have to start that process over. So that potentially could be problematic to the collection procedures. So in conclusion, regulating the temperature in the liner and reducing the amount of perspiration can lead to improved comfort. And the results of this study support continuing the evaluation of the PCM liner as a potential means of regulating skin temperature and potentially improving health and quality of life for amputees. Quick look at some references, and thank you for your attention, and I'll be happy to answer any questions.